rotational kinetics. And before I get into the kinetics, so remember when we talked about translational kinetics, particle kinetics, before we did that, we had to talk about particle kinematics. And so we defined velocity and acceleration and position and all that stuff. So first, before I can talk about rotational kinetics, I have to define the angular velocity and we're going to, the variable we're going to use for that is the Greek letter omega. That's a lowercase omega. And angular acceleration. And the angular acceleration, we're going to use the Greek letter alpha, or Jesus fish. Okay, so angular velocity. So the angular velocity is a directional quantity tells you how quickly an object's orientation is changing. And sometimes it can be a little confusing. There are a lot of similarities between circular motion and rotational motion. So I want to be, before when we were talking about circular motion, we were talking about a particle doing this. We didn't care about the orientation, turning or not turning, changing orientation or not. But the thing is, like, if you think of my location as a point, that point is going around in a circle. And now with rotational motion, I'm not talking about whether I'm moving, the point that you choose to define where I am is moving in a circle. It's just about whether my orientation is changing. So before we were talking about this thing, now we're just talking about this thing. Okay. And you can have both of those happening at the same time. But we're just talking about you take one reference point and see how quickly it goes from this orientation to this orientation, And we're going to use angles in radians now for this, which is a nuisance. You don't have to change your calculators because we're not going to use cosine and sine for it. But my angular speed then is per second how many radians I rotate through, So what one full revolution, how many radians is that? 2 pi. So if I'm doing 1 RPS, rotation per second, then my angular speed is 2 pi radians per second. Okay. If I'm going half that fast, my rotational speed is pi radians per second. Okay. So the magnitude of the angular velocity is how many radians the orientation changes per second. For example, let's say you have a boat that goes through, what's a reasonable RPM for some kind of engine, boat engine? 10,000? Let's say. Okay, so boat engine goes through 10,000 RPM. That's rotations per minute. What's its angular speed in radians per second? Well, each rotation is 2 pi radians. And each minute is 60 seconds. So if we start with 10,000 rotations per minute, convert rotations to radians. One rotation is 2 pi radians. And 1 minute is 60 seconds. So you get 10,000 times 2 pi over 60. Can someone divide that for me? A little over 1,000, right? $1,047. Point what? Okay, that's good. Okay, so radians per second. So something going 10,000 RPM. What? That's in there, right? Yeah. So pi is about 3. So if pi was exactly 3, it would be 1,000. Any questions about that? Okay, so that's what the angular speed is. But angular speed doesn't have a direction. Angular velocity does. The sign of the angular velocity gives the direction. Positive is counterclockwise. And negative is clockwise. You might think it should be the other way, but we didn't get to choose. Okay, so let's say we have top. Spinning clockwise with a constant angular velocity. And it makes 10 full revolutions each second. What's the angular velocity? So actually, let's take a minute and why don't you try to do this together? And after I give you a few minutes, I'll go through it. Let's see if you can. Okay, so every second it makes 10 revolutions. So you can think of that as 10 revolutions per second. So if we have 10 revolutions or 10 rotations, means the same thing, per second. One revolution is 2 pi radians. And so the angular speed is 10 times 2 pi, so 62.8 something. Radians per second. That's the angular speed. That doesn't have any direction attached. So now we have to include the direction. It's spinning clockwise, so what's the sign? Yep, so negative 62.83 radians per second. The angular velocity doesn't have to be constant. Angular velocity can change. Watch. That actually made me pretty dizzy. Oh, you get dizzy really fast when you get old. Okay, so so the angular velocity doesn't have to be constant. So what do you think you call the thing that determines how quickly the angular velocity is changing? Angular acceleration. Angular acceleration is a measure of how quickly the angular velocity is changing. It's totally analogous to the way velocity and acceleration are related for particle stuff, for translational stuff. So what do you think the angular acceleration is for something that has constant angular velocity? Right. So constant angular velocity is equivalent to 0 angular acceleration. And who can come up with the mathematical definition of angular acceleration? That's a hard one. Yes, do it. I'm going to change the subscripts. So you're on the right track, but this is the way, and we haven't really used this equation much, but this is the same definition that that we had for the relationship between acceleration and velocity. And in fact, it's the limit as t2 minus t1 goes to 0. We're never going to use that again. What? Yes, right, it's calculus. But yeah, so we won't say calculus anymore. It was Angela who brought it up. Yeah, exactly. Yeah, there's a wide range of emotions that calculus brings up for people. Okay, so angular acceleration is directional. And the direction is given by the sign. So what do you think is the relationship between the signs of angular velocity and angular acceleration if something's rotation is speeding up? Same sign, yep. So omega and alpha have the same sign if the rotations are speeding up. And omega and alpha have opposite signs if the rotations are slowing down. And like I said before, if alpha is 0, then the thing has a constant angular velocity. The angular velocity isn't changing then. Okay, so that's all we need of rotational kinematics. Start talking about rotational kinetics. I want you to notice there's a strong similarity between the relationships of V and A and the relationships of omega and alpha. Okay. And so I want to write this table of these. So in one column of the table, I'm going to put all the translational stuff that we're used to. And in the other one, I'm going to put the corresponding, like, analogous rotational things. So here are the translational, or I'll call them the particle variables and relationships, and these are the angular ones. So we've seen that velocity is similar to angular velocity, and acceleration is similar to angular acceleration. And we've seen that the acceleration, the definition, see, is defined as this. And we have that exact same relationship for the angular acceleration. And we've seen that if these two are in the same direction, it means the thing's speeding up. Same with these angular properties. No, don't encourage it. He's just looking for attention. And if they're in the opposite direction, slowing down. Same thing here. Okay, so that's a lot of major similarities. But what I'm going to show you next is going to blow your mind. Each one of your minds. Maybe not at the same time, maybe like more like popcorn. Like, you know, like okay, so first I have to just tell you the new sort of analogous variables. So for particle kinetics, we had this mass m, you know. For rotational kinetics, we have this capital I sub a, and that's called the mass moment, this has a long name, of inertia about axis A. We'll end up just calling it the moment of inertia for short. But just like the mass for particles is a resistance to acceleration, right? Like if you apply a force to something, how much it accelerates depends on how much mass the thing has. This mass moment of inertia tells you how resistant something is to angular acceleration. So if you try to turn something and it has a big mass moment of inertia, it's going to be hard to turn. If it has a small one, it's going to be easy to turn. And for particle kinetics, the thing that you apply to something to try to make it accelerate is a force. for angular kinetics, it's called M sub A. And that's called the moment about A, or sometimes people call it the torque about A. Torque and moment mean the same thing. You know, this is the axis A again. Okay, now get ready for serious popcorn brain. The equation that we use for particle kinetics is F equals ma. For angular kinetics, the angular version of the force, this moment about A, is equal to the angular version of the mass, I sub A, times, what do you think? Angular acceleration. So all this stuff is super easy to remember anyways, because you've seen all these relationships before, you know? Like basically every relationship you had for particle quantities work for angular quantities too. Okay, well, so all we have left before we can use this rotational version of Newton's second law is I have to define how you calculate the mass moment of inertia, and I have to define how you calculate a moment, and then we can put it all together into calculations. So before we can use the rotation, let me call it angular. Before we can use the angular version of Newton's second law, we have to define the mass moment of inertia IA and the moment about A, MA. So first, the mass moment of inertia mass moment of inertia about the axis A. And the calculation for this okay. So let me first just give sort of a intuitive definition. So this is a positive quantity, just like mass was. That's large if an object is hard to rotate. And small if an object is easy to rotate. A high value of I sub A occurs if a lot of mass a lot of the object's mass is distributed far from the axis A. And a low value of I sub A is when most mass is distributed close to the axis A. Okay, so here's another good gymnastics example. So if you're going to do like a double flip, you know, there's all these different ways you can do it. And two of these ways are ones like this. Let's see. Head banging is going to get annoying soon. Okay, so one is like this. And then another way is like this. These aren't like the only two ways, but okay, so this is called a tuck, and this is called a layout. And okay, so if you're looking for a way to get a lot of points, you get a lot more points, a lot more, for doing a double layout than you do for doing a double tuck. And the reason for that is it's the same person, so it's the same total amount of mass. If you think of, in this case, the axis of rotation is the center of mass of the person, so I'll label, there's the center of mass there, here's the center of mass here in this case. The question is, how is that mass distributed around the axis of rotation? In this, all that mass, the person's pulling all that mass as close as possible into the center of mass. And so the mass moment of inertia around that axis is relatively small. In this one, the person's spreading the mass out almost as far as possible from the center of mass. And so the mass moment of inertia here is high. So it's easy to get this rotating and hard to get this rotating. Okay. And so the effect of that, I guess the main thing is, it makes this harder, is since this is going to rotate a lot more slowly, you got to get a lot higher up in the air to do two flips that way than you do to do two flips this way. Okay, this is so this is a low mass moment of inertia. Easier to rotate. And this is a high mass moment of inertia. Easier to rotate. Okay, I forgot to bring this with me, but I'm going to go get it because it's worth it. I'll be right back. So that's the mass moment of inertia, and I guess I'll give you, I think I'm going to give you one formula here. So the mass moment of inertia for a rectangle It depends on where the axis of rotation is. So say here's the rectangle, and you can rotate it, you know, you can imagine taking a board like this and just like nailing it to the floor or something, you know, think of this as a top view so that it's free to spin. You could put that nail here and spin it. You could put the nail here and spin it. And so all of these different places are possible locations for the axis of rotation. But I think the only ones we're going to need are like this. Actually, let's do one here too in the corner. Okay, so the mass moment of inertia, if you're rotating it around A, is 1/12 times the mass of the rectangle. I have to get 2 dimensions here. We'll call that L and this W. Times the quantity L squared plus W squared. That's if the axis of rotation is the center. If the axis of rotation is B, then you have 1/3 mass times length squared plus 1/6 mass times width squared. And if the axis is C, then you have 1/3 times the mass times the quantity L squared plus W squared. So of those three, what would you guess just intuitively? Which of these is easier? Is an easier rotation? A, B, or C? A. Yep, that's you. You can't choose an axis where the material is more like without changing the shape, where the material is closely pulled in around A. What do you think's the second? Oh wait. Okay, ready? Okay. What do you think's the second easiest? B. And it really just has to do with like this is the easiest spot. You can't find any easier one, and it's just how hard it is has to do with what the distance is between the easiest spot and where you are. So easiest, next easiest, hardest. Okay, and so the biggest value is IA. The next, no, sorry, the smallest value is IA. The next smallest value is IB, and the biggest value is IC. Okay, so now we have to talk about the moment or torque about an axis A. So we just have this random shape. And let's say this is the axis. And now let's say we have another point, I'll call it P, where a force is applied. Okay, so I'm going to draw a line between those two. And let's say the force is applied this way. If the force vector is perpendicular to the line between A and P, then the absolute value of the moment about A is equal to the absolute value of the force times the distance between A and P. Okay, so this D is the distance between A and P. And if I draw it up here, this here is D. And then the sign comes from thinking which way would force make the object rotate. So let's go up to this example. So if this object could rotate freely around this axis A, and you applied a force here, would that body rotate clockwise or counterclockwise? Yep. So just like the sign convention for angular acceleration and angular velocity, counterclockwise is positive, clockwise is negative. So once you knew the magnitude from multiplying F and D, this would be negative. So counterclockwise is positive. Clockwise is negative. And that moment is, it works for angular motion the same way a force works for translational motion. If you apply a big force to something, it's going to accelerate a lot. If you apply a big moment to something, it's going to have a big angular acceleration. And intuitively, I think the easiest way to make sense out of it is, say you have a bolt that you're trying to turn with a wrench. So if you're trying to loosen this bolt and it's stuck, you're trying to turn it this way, okay? And here so say that no matter where you apply this force, you're gonna apply 100 newtons of force to the wrench. Well, where are you gonna get the best result for loosening this? here, that would never, if you applied it right here, you could apply a million newtons of force. It would never make this thing turn. All it would do is eventually rip the bolt off the wall. Apply it here, you get an intermediate result. If you apply 100 newtons here, that's what's most likely to cause that to rotate. And that's the relationship that the moment calculation gives you. It's not just the force. It takes into account the force, because the harder you push, the more likely you are to turn it. But it also matters where you apply that force, how far from the axis you apply that force. Okay. So if you apply 100 newtons here, you get a big moment. Here, you get a smaller moment. And here, you get 0 moment. It's not going to rotate it at all.